So today, the plan is to learn this, adder arithmetic circuit. So if we go back to the content, okay, so 3.3 is the arithmetic circuit. Where we will learn today is the adder, subtractor, comparator, and multiplier is for you to learn on your own after you have learned this. So we will start with adder, okay, today. And I think last week we have learned a simple adder. I'm not sure whether both sections have learned this already or not. But today maybe I can repeat this such that you can refer back to this class, because the class is recorded. Okay, so you can refer back to this recorded class and do the revision and do on your own later on. Okay, for the preparation for the test, can. Okay, so adder, half adder, I think you have done in your assignment. Okay, so today we will look at the full adder. They used to add multiple bits or bigger number than just a 1-bit number. So for example, this is a 4-bit adder where you can add 4-bit number x and y and get the result, the sum result as. Okay, so to do that, you need to create a 1-bit adder first, 1-bit full adder based on the truth table. So from the truth table, you can create the K-map to derive S and also to derive C I plus 1 or C the carry bit. Okay, so this is the equation. So from the equation, you can create a 1-bit adder like this one. This is 1-bit adder, 1-bit adder, and then you can connect like this and to form or to create a 4-bit adder or even a bigger adder, right? So let me demonstrate. I think we take this opportunity when we learn online. So it is better to give you demonstration on using the quarters such that you can use this to learn to recreate the same circuit. All right, the same design. Okay, so let's use the quarters. So this is the 1-bit adder. So we will design this 1-bit adder and then use this 1-bit adder to create this 4-bit adder. Okay, like this. And because the code is already here, so I can just use this code in the quarters. So let me open quarters. Right. Okay, so this is the quarters. So we want to try to create that. So remember, when you have the quarters, you can when you want to design, you need to create a new project. Okay, so I will go fast in this tutorial. So you can use this as your reference later on when you do your own exercise, right? Because we don't have time to do this. Everyone do at the same time. It's not a good practice, right? So I will go very fast in this tutorial, but you can use this later on to learn from this tutorial. Okay, so when you create a new project, you go to next, of course, and then create the folder that you want to save your design. So in this case, I will actually I have the adder. Let me have a new one. I call this adder number 2. And now I want to do this. I want to create this 1-bit full adder. All right, this module first. So I call this project as FA full adder, or maybe I use this FULL ADDR. Okay, the name is full adder. I can click finish now because I don't want to add anything up to my design right now. So click finish. So I create a project. Okay, so I have this. So of course you need to write the code here. In this case, I just copy the code from the slide. Okay, and I paste here. But of course, the name is not FA. In this case, it's full adder. You see this? Full adder. So it should be FULL. FULLADDER. Okay, so everything is the same. And then you can save this. Full adder name must be the same as your design name, module name here. Okay, click save. Right. So after you save, you can do the synthesis, or a faster option is to use the analysis and elaboration. Okay, like this. Okay, for the fast check. Okay, you can see that this no errors, one warning, and this warning is okay. We have discussed this warning already, so no need to explain again. So this is okay. I think we don't have to test this. Yeah, this is simple. This is correct, already tested, so no need to write the test band for this one. But in your case, if you want to write the test band for this, you can do that. Okay, but in this case, I will not write the test band, so I will leave this to you to write the test band for this. Okay, so I have done with the full adder design here. Now I want to create this, and this is the code. Right, so I need to close this project, close, and I need to create a new one. Okay, next, adder 2. In the adder 2 is the full adder. So maybe I create a new 4-bit adder. Maybe adder 4-bit adder. Full adder 4 to represent a 4-bit adder. Now I need to go click next here. This is empty project. Now I need to add the file, the full adder that I just created just now, which is this, this one, full adder. Click OK. Now make sure that this full adder is in the library, right? And you can go next, or you can finish now. Okay, so if you miss this tab, don't worry, you can add later after here by go to assignment, go to setting, and go to file, and you can still choose your design file that you want to include in your new design like this. Yeah, just do that. Okay, so now we need to create a new one, new Verilog program. So this is the Verilog program. So in this case, again, I want to use this one. So I just copy this all to here. Okay, now I have this. And the name, of course, I need to change to full header 4. Okay, and again, this one, because our top module, our sub module, the FA, the full header that we designed just now is not, the module name is not FA, but full header, right? So this one must be full header, same as this one, same as this one, and also this one. The rest is the same, and this is called the port position name syntax, right? How you connect your wire to create this. So in this case, let's discuss on this. Okay, or maybe I can use this one. So in this case, the connection is built by referring to the module FA. So for example, if you want to create this one, right? So we need to look at how the port is arranged in the FA module. So in this case, it starts with X. So meaning that in this one, we need to start with X0, right? Connect to X here, and then followed by Y. So this is Y, Y0, connect to here. CI, because this is CI, of course, this is CI. And then CO for this one is connect to C1. That's why we have C1 here. And lastly, we have S connect to S0s. That's why we have S0 here. Okay, now we have this one. Next is the second module. Again, X is now connect to X1. That is why we have X1. Y connect to Y1, Y1. CI in this one connect to C1. That is why we have C1. CO for this module is connect to C2. That's why we have C2. And of course, S is connect to S1. We have S1. For this module, X2, Y2, X2, Y2. CI is connect to C2. That's why we have C2 here. Cout connect to C3. That's why we have C3 and S2, of course. And the last module, X3, X3, Y3, C3, C3, and then CO, Cout, this one, Cout, and then S3. So we have all the module already. And if you look at this, so it should be complete now. So we save as the full header 4 name, click save. And again, you need to do the analysis and elaboration, or analysis and synthesis, either one, and wait for it. Okay, looks like everything is okay. So now we can test, check whether our design is correct or not by doing the simulation. So to do the simulation, of course, you need to write the attachment. So let's write attachment, create a new one. And of course, if you want to write attachment, again, let's do some revision on the attachment. And remember, next week is the test. So you should know how to write attachment. This is important. When I say important, this is important, right? I think this one is 3 times important. Okay, let's look at how we create attachment. Okay, this is our new 4-bit adder. And this module is named FULLADDR4. Okay, make it bigger. And you will have the output called as, you will have the CI, CIN, you will have the CO, and you will have input X and input, is it capital letter? No, small, X, Y, C, I, okay. So it should be X, Y, like this. So this is the module that we have just created. Now, we need to create attachment. Means that we create a new module like this. And let's call this module as FA4 test. All right. And of course, we need to have the connection here, here. And let's call this as capital X, capital Y, and then this one, the output, let's call this CO also, but C capital. And then we have this as input. And let's call this CI also, but C capital. And we have the output as, and this is S capital. And of course, this one is 4-bit. We have 30. This one is 30, 4-bit. CI and CO is 1-bit. And we have this 30, 4-bit. Okay. So this is what we want to do. And of course, this test module, the module that we just built, the FA4, is, we will call this DUT, or design and the test. Okay. So we want to create this FA4 test module here. Okay. And again, for the attachment, we need to have the time scale and I will use 1 nanosecond to 1 nanosecond. So I have explained this in the class. Okay, so you need to know this also before you go for the test. Right now, just like when we create the Verilog module, so we need to have a module name, and the name is in this case is FA4 test, FA4 test. Okay, let's use this name, right? And we will have I think I have this so that you can see, compare 1 to 1. Okay, so this X we now not call as or declare as input in the attachment, but we will use or declare this X and Y as rag, yeah, and as we will declare as wire, and this is rag also because this is input to the module, and this is output from this, so we will or declare this as wire, right? So we have rag 4-bit X, Y. We have rag CO, CI. CO is not rag, right? Only CI. We have wire S. We have wire CO. Okay, done. And then what we want to do is we want to instantiate this, right? Means that we need to have a module instantiation. So the name of this module that we want to put in is full adder 4. Adder 4, and the name for this attachment is DUT, design the test, is DUT. And we do the connection. So the connection will be based on this. We will use the positioning syntax, or you can use the port name connection as well. You can use dot x, small x, connect to x, and then dot y, connect to y. But in this case, I will show you how to use the port connection syntax, where we will use this, follow this connection, where we have x, y, to x, y, x, y, x, y, ci, ci, co, and s. CO and S. All right. So this is how we have this in the test module. Okay, when we have this already, now we need to give the input to the X and Y and observe the output at S. Okay. So we will use the initial block. At time 0, that's our X to be 0 and Y to be 0, and CI is 0. Right. at 20 nanosecond, we change x to 2. And let's see what happens. Should be x2. If y is still 0, means that the output s should be 2, because 2 plus 0 should be 2, right? So the result, x plus y, should be equal to 2 here. Here, the result, or we can say that s should be equal to 2 here. Here, s should be equal to 0. Next, we will have x. Maybe x is the same. We just change y to maybe 1. Now here, our s should be equal to 2 plus 1. Should be 3, right? And then at 60, so let's change x to 4. 4 plus 1 should be 5, right? Because y equal to 1. So now s should be equal to 5. So, okay, let's stop. This should be 20. 20 should be at the same time. If you say 40, means that it will happen at 60 nanosecond. Okay, so we use 20, means that the signal change the value every 20 nanosecond. Now let's stop the simulation here. Okay, so a simple simulation file to test the design. Okay, and let's see whether we have a correct output or not. Right, so first we need to save this file as fa4 underscore test. Save this. Save. And then let's check whether our code is correct or not in terms of syntax. Just double check. Okay, so far so good. So we do the simulation setting. So you go to the setting, go to the EDA tool setting, simulation, choose the Altera, model sim Altera, and then go to top compile attachment, create your attachment, create a new. The attachment name should be the same as your file test file name, and then you need to add that test file to this. Click add, such that it is listed here. Click OK, OK here, and go OK here, and then you run the simulation. This is functional simulation, or we call it RTL simulation. Okay, so we wait until we have model sim is executed. So we wait to finish. So and look at the window. Okay, so we can see that this is can you see this? You cannot see. Wait, yeah. Okay, hope you can see this. All right, so we have x, y, ci, as. Okay, so this is in binary by default, but I think it's good for us to see in decimal. So we can change the x, y, and s to decimal. Ci and Co is 1 bit. So it's no need to change to decimal. 1 bit is 1 bit, only 0 or 1. But x, y, and s, we can change the radix to decimal. Okay, so you can see the output here. When 0 plus 0, you have 0. 2 plus 0, you have 2. 2 plus 1, you have 3. 4 plus 1, you have 5. So this is how we verify or test whether our design is correct or not. Of course, in practice, you need to have more test vector to make sure that your design is correct. This is too few, too small. The number of test vector is very small. So this is not guarantee that your design is correct, but so far so good. Okay, because the design is small, so it's easy to check. Oops. Okay, so that is adder. Right? Full adder. So if you want to have a bigger adder, you just add here, right? You can add up to the number of bit, the size that you want to have. For example, if you want to create an 8-bit adder, so you can instantiate the FA module 8 times, right? Or you can even have a bigger than that, right? So that is adder. So now how to subtract number? Okay. Before this, we add, and the next one is we want to subtract, minus, right? So same thing. So we need to create a circuit just like this. So in adder, we need to have the truth table, and then from the truth table, we can get the equation and so on, right? To create something like this, to have the adder. But for subtractor, we have the option. Actually, we can do the same way, where we can create the truth table and try to do something like this to get the result. But this is not straightforward. This is not so easy, because adder is subtractor is in subtractor, we have something called borrow, right? For example, if the number we want to sub from, okay, the smaller number, like for example, okay, like this, in binary, let's say we have 0, 0, 1, 0, like this, okay, 4-bit. Now in add, if this is add, this is easy. 0 plus 1, so we have 1. 0 plus 0, we have 0. And we just have a carry, right? 0 carry here and 0 carry here. But what if this is subtraction? 0 sub 1. So you cannot do that, right? You need to borrow from here. And this one also, you have borrow. You cannot borrow. You need to borrow 1 from here. So in digital, it is not easy to do that. Okay. So that is the problem in digital. So we need to find other way to do subtraction in digital, right? Maybe we can do like something like this. Let's say we have 5 minus 2. Of course, easily, we are human, we can get the result straight away. 5 minus 2 is 3, right? But how to do this in hardware? How to create the circuit to do this operation? So maybe we can do something like this. 5 add, because we have the adder, right? We have the adder. We have the adder circuit, right? So this is good. And instead of 5 minus 2, why not we do this? 5 add minus 2. And we get 3. Okay. It's a very promising approach. But the second question is how we represent a negative number in digital system. Okay. Because in decimal, negative number is represented by the minus sign. Minus 2 is negative 2. Positive 2 is positive 2, or just 2. This is positive 2. So far, what we have is we can represent a positive number in digital, right? For example, if our system is 4-bit, so positive 2 is 0010. Okay, that is positive 2. But what if negative 2? Do we write something like this? Minus 0010. The answer is no. How you create the negative in hardware? You cannot do that. So the answer is you need to use the 0 and 1 to represent sign as well, right? Because we use transistor, remember, for digital system, the MOSFET transistor. And this will give you only 0 and 1. Okay? So how to represent negative number? And again, we use negative 2. The idea is, have been proposed long ago that, okay, we have 4-bit number, for example, number 2 is 0010. And let's use what we call the sign and magnitude representation. Okay, where we will use 1 bit, the most significant bit, or MSB, as a sign bit. We call it sign bit, and the rest after that another 3 bit in this 4-bit system. 4-bit system. If our system is 8-bit, so number 2 is like this, 8-bit. So this MSB is the sign, is used as the sign, and the rest is the magnitude, right? So that is the concept. And let's represent positive using 0, or 0 indicate that the number is positive, I mean, for this MSB bit, right? The sign bit. If 0, this is indicating that the number is positive. If 1, this number is negative. It's look good for now, right? For example, if we are talking about positive 2, so the number should be, yes, should be like this. Should be 0, 0, 1, 0. So this is positive 2, right? Because the sign is positive and the magnitude is 2, positive 2. Now, if the number is like this, 1, 0, 1, 0, and the sign is 1, means that this is negative, and the magnitude is 2, so this is negative 2, right? So it looks good. Now, whether this technique or this system can be used in the subtraction or not, we need to test. Now let's test, yeah, take this into the test. So again, we will use 5 plus minus 2. So 5, when we represent in binary, is 0. This positive, this because this is positive 5, so it should be 0. The magnitude is 101. So this is, of course, positive 5. Add. So we use adder. And remember, we have the adder circuit. Minus 2. Minus should be 1. Right? Negative. 2 is 0, 1, 0. So this should be minus 2. Right? And now we add. Remember, we add. Yeah? So we add. Let's add this together. So 1 plus 0. So we have 1. Of course, we will have the carry, 0. 0 plus 0 plus 1, we have 1, carry 0. 0 plus 1 plus 0, we have 1. We have, again, the carry is 0. And we add again. And of course, we have the carry 0. And because our system is 4-bit, so we ignore this. Okay, so this is the result. Whether this is positive 3 or not, let's check. All right. Now you see the sign. The sign, this is negative. Something wrong already. All right, because we should have the result should be positive 3. But now the result is negative. It's not good. And you see the magnitude? This is 7, right? Negative 7. The answer should be plus 3, but we have negative 7. So, conclusion. The sign and magnitude representation is useless. You cannot use this. Okay, the negative number cannot be represented using sign magnitude representation. This is a problem. Now, the engineer is not stopped there, not give up on this. So remember, when you learn digital electronic, you have another number system. We call it first complement. Or even second complement. You have another kind of binary number representation. We call it first complement and second complement. So the first part is first complement. First complement is easy. The concept is easy. Where, for example, if you have number 1, 4-bit, is this. When you do first complement, means that you convert or invert each bit to the opposite logic value, right? Like, for example, 0 here. When you do first complement, you will have 1, 1, 1, 0. So this is the answer, the first complement of number 1. And for the second complement, number 1, we can represent to what we call the second complement representation by finding the first complement first, which is again 1, 1, 1, 0, and then we add 1 to the first complement number, and then we have 1, 1, 1, 1. So this is the second complement of number 1 represented in 4-bit. We have this number system, right? You have learned this in digital electronic. Now, can we use this? Let's start with the first complement. To represent negative number. So let's use first complement to represent negative number. First complement to represent negative number. Okay, like for example, -2 just now. Okay, -2. If we take number 2, which is 0, 0, 1, 0 in 4-bit, and then we find the first complement for this, which is 1, 1, 0, 1, right? And we say that this is -2 represented in first complement. And let's do the same operation like this. Now, we have positive 5, which is 0, 1, 0, 1. And then we add 2, -2, where we will use this 1, 1, 0, 1 to represent -2. Now let's add 1 plus 1, we have 0. And of course, we have carry 1. 1 plus 0 plus 0, we have 1. 0 carry. 0 plus 1 plus 1, we have 0. We have 1 carry. 1 plus 0 plus 1, we have 0. And we have carry 1. And of course, again, because our system is 4-bit, so this is the answer. What is this? This is positive, of course. Again, this is still representing the sign, yeah? 0 means positive, and 1 means negative. Okay? So the sign is positive here. Positive is good. And look at this. This is 2. And we know that plus 5 minus 2 is equal to 3. This is 2. It's not correct. But what if we take this and add to this result? What happened? So when we add 0 plus 1, we have 1. 1 with plus 0, we have 1. And then 0, 0. And this is, of course, positive 3. And this one is 3. Look, good, right? It looks good. Now let's test for the maybe other value. This may be a maybe just fluke, right? So let's use the value like let's say 6 positive 6 minus minus 1. So it should be 5, right? So again, when we use this, we will do 6 plus minus 1 to be equal to 5 minus 1. 6 is 0, 1, 1, 0 in binary. Minus 1, now we use negative first complement representation. So 1, 0, 0, 0, 1. When we change to first complement, so we will have 1, 1, 1, 0. So this should be minus 1. So we add, because this is add, minus 1 is 1, 1, 1, 0. Now let's add. 0 plus 0, we have 0. 0 here, we have 0 here. 1 here, right? We have 1 here, 1 here. 1 plus 0 plus 1, we have 0, 1. And again, we have this. And this carry, let's add to here. So we have 0, 1, 0, 1, which is 5. And this is 5. So this is look good, actually, right? Look good. Because it can give us the subtract operation, subtracting by using adder. But the problem is that you have this add all the time, right? You need to add the carry to the result to get the correct output product. And remember that we have where is that? We have another system that is called a second complement. Second complement, right? The previous one is first complement. Now let's use second complement to represent negative number instead of first complement. So again, I will use 5 plus 2, 5 minus 2, okay, where it is actually 5 plus minus 2. And see what happened. When we represent this minus 2 by the second complement of 2. Okay, again, 5 is 0, 1, 0, 1 plus minus 2, second complement of number 2. So number 2 in binary is 0, 0, 1, 0, 4 bit. Let's find the second complement. So to get second complement, you need to find the first complement, which is this, and then add 1. And you will have 0, 1, 1, 1, 1. So it should be 1, 1, 1, 1, 1, 0. And you see the sign, yeah? This is minus. So 1 still represent minus, and 0 still represent plus. Now we add 1 plus 0, we have 1. 0 here. 0 plus 1, we have 1. And we have 0 here. 0 plus 1 plus 1, we have 0 here. 1 here. We have 0 here. 1 here. And let's see. So this is, of course, plus 5. This is minus 2. And what is this? This is clearly plus 3. So you see, 5 minus 2 is 3. And we just ignore this, right? Because this is scary, we just ignore this. Our system is 4-bit. So 0, 0, 1, 1 is plus 3. This is very good. Now let's look at the second example. If we have 6 minus 1, should be plus 5, right? Because we have 6 plus minus 1. So 6 again in binary is 0, 1, 1, 0 in 4-bit. Minus 1, when you change to second complement representation, is 1, 1, 1, 1. 4 minus 1. When you add 1 here, you have this. You have 0 here, you have this. You have 1 here, and you have this, right? And you will have this. And again, this you ignore. And look at this. This is positive 5. Positive 6 minus 1. The answer is plus 5. So, conclusion. We can use second complement to represent negative number. And this is actually universal, right? In your computer, the negative number is actually represented by the second complement representation. So you can check that, and you can use your calculator, for example. So in this case, let's use the calculator, right? So I can use the calculator in the computer. So you can use, if you want to use the computer calculator in your PC. So you normally it will show you the standard version here. But if you want to use the base one, you go to programmer. Here, this you can see in hex, decimal, octal, binary value. Okay, so just like in your when you use your calculator, right? Calculator, you can use the base. Yeah, if you can see this, yeah, on the screen. Okay, so in this case, when you write in decimal minus 1, right? When you convert to hex binary, you can see that, see, all are 1. Because this computer is 64-bit, so you can see that you will have all 164 number. So this is minus 1 in 64-bit, right? You can check on your calculator. For example, in my calculator here, of course, I can use this the calculator. Oh, I don't have now. Maybe I can install the calculator. If you want to install in on your phone, right? So you can use this one. Search for real. This one. Yeah, this one is a free calculator. Of course, you will have the paid version. So I will install this. Juice coffee also here. Okay, it's done. So right, this is the calculator. So maybe I want to show the predict mode. Okay. Yeah. So I have this value. So for example, if I -1, right? So this is -1. So I change to binary. So you can see that all are 1. Okay. So my calculator can show up to 12 bit, right? 12 bit. So you can see that 1, 2, 3, 4, 8, 12. 12 bit. So this is -1 in 12 bit. So we can verify that if the number is 12 bit, okay, -1, yeah, 12 bit. So one in positive positive 1 in binary is binary 12 bit is 00000000001. Now try to find the second representation, second complement representation of this number 1, 12 bit. So of course we need to find the first complement, which is 1, 1, 1, 1, 1, 1, 0. Right? This is the first complement. Now to have second complement, you just add 1 to this first complement value, right? Now you have 1, 1, 1, 1, 1. So this is -1, 12 bit. Just like in my calculator, right? This -1. If for -2, right, for example, -2 should be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, right? So if we change to binary, so this is -2 in binary, which is second representation of number 2, 12 bit. Okay. So that is how we create a negative number in digital system. Now, how to create the hardware for the subtractor? Okay, if we know that, we can use now the second complement number to represent the negative number. So again, let's go back to the example. 5 plus -2. Or we can say that x, if we use the variable, right? So we have x minus y. So actually what we do is x plus minus y, right? Where minus y is actually second complement of y. In other words, we can say that in logic equation, right? This is s, s. So s is actually x plus minus y is actually complement of y, which is not y, plus 1, right? Is that true? because minus y is actually second complement of y. Second complement of y, okay, where we have y, to find second complement of y is to have not y plus 1. Is that correct? Yeah, because if y equal to 1, for example, right? 0, 0, 0, 1. Second complement of y is 1, 1, 1, 0, right? When you plus 1, you will have 1, 1, 1, 1, which is minus 1. So this is our conclusion. Now, how to create the hardware? The answer is not that difficult because we have created the adder. So now let's have our 4-bit adder again. Like for example, we have the 4-bit adder. Let's create the 4-bit adder. Of course, we create from the smaller 1-bit adder. So we have X, we have Y, we have S, we have CI, we have CO. Okay, so this is FA. Make it bigger. FA, Y, CI, S, right? So we want to make this 4-bit. So this 1-bit, we will have now 4-bit. Okay, so this is 4-bit adder. So X plus, and this is actually plus. So this is plus, this is adder. So let me label this as plus adder. And this adder will always do X plus Y and give you S output here. So X is just X. So we can have this as X. In this case is X3. This is X2. This is X1. This is X0. And the output S is done. So this is should be S3. This is S2. This is S1. And this is S0. CI is just CI. And again, this is the same. And we have C out. Should be no problem. But this one, why not? How to get why not? The answer is you add the inverter. You add the inverter, you get why not here? Y0. This is Y0. So this should be Y0 bar. See? And again, here also the same. You will have Y1 here. Here you will have Y1 bar. Here also the same. Here also the same. Okay, now we have Y bar already. So this is X plus Y bar. So this is X plus Y bar, right? Because this is all our Y bar. Okay, what about plus 1? How to get plus 1? The answer is at the first adder here, because this adder module will add this to this and add this one. This one add, this add, at this one. So the CI, we will give number 1 here, such that this will be added to this one to get the y bar plus 1. That's it. And we get the subtractor. So you see, this is a subtractor because it will perform this function x plus y bar plus 1. And the output s will be actually x minus y. Right? Okay. Now we have learned how to design an adder and also the subtractor using actually the adder. Right. Now before the break, let me show you how to create this in hardware. Okay. So maybe I can use the same circuit here. Okay. Because we have this already. What I want to change here is to change this to not. All right, to represent this not. All right, so I put this as not. Now this circuit become a subtractor already. Okay, and of course in the simulation we will give Ci equal to 1, and we will have the subtractor circuit. Right? Let's see what happened. Save this. Now, of course, I want to close this first. The previous simulation. Okay. All right. Nothing wrong with this. The attachment, Ci now we change to 1 to get this. Right. So it's now 1. I think you need to do the. Oh, yeah. Let's have the x is 5, y is 2. Okay. So now we should have here the result as should be 3, right? 6 y equal to still 2. This x equal to 7. 6 y equal to 1. So the s should be equal to 5. Right? 6 minus 1. 7 minus 1. So s should be equal to 6. Okay, because y still remain 1. All right, save, and let's run this. Not yet finished. Okay, so we have already here. Now let's change this to decimal such that we can see the output. Okay, so 0 minus 0, we have 0, right? 0 minus 0, we have 0. 5 minus 2, we have 3, see? Minus, this is 5 minus 2, we have 3. 5 minus 1, we have 4. 7 minus 1, we have 6. So this is subtract operation using the adder. Yes, adder. This is adder, right? But we change this to not y to get the first complement. And then C1 equal to 1 to add 1 to get the second complement. And we have the subtractor already. And this is what in your computer. Okay. Any questions so far before we take a short break, 5 minutes, and I will take the attendance. So only 50 minus 2, 48 coming today. Many of you are not coming to the class. Nanti test tahulah. Okay, any question?
No, doktor.
Doktor, saya ada.
Ada?
Yang dekat test bench tadi tu kan?
Test pen, okay. Okay, test pen.
Yang dekat 40 nanosecond tu memang dua-dua Y ke? Y equal to 6 dengan Y equal to 1.
Tapi dia keluar apa? Kat sini.
Dia keluar tadi betul je kan?
Y saya tak kejap Y tengok betul tak dengan apa yang keluar kat sini. Wait ni Okay, we have x00 52 y6 y1. Dia ambil yang mana? Dia ambil yang 1. Kan? 5 ni yang 6 y6 tak ada, tapi x remain 5 lah. So actually what I want to do is x here kan. But this is correct. I mean, this will the graph, the timing diagram here will be plotted based on what you write, what you wrote here. So exactly this from this lah. You see, y6, y1. So it will take the last one. Y equal to 1. You see, that the y equal to 6 because it happened at the same time. Ni at the same time ni. Faham tak?
Faham.
So when you write like this, it will take the last one, the last value. Letak kat sini 1. So 6 tu tak ada lah. But what I want to write actually ini adalah 6. And let's change this, and then let's close this lah. Close this. Close this. Okay, and run the simulation again. Ni faham X. Maksudnya X. Ni X6, Y1 lah. And then let's run again. Okay, bagus. Means that you spot something. I mean, just a mistake that we write in the attachment. It will plot the value that you write there. Where is it? Now, if we show the one that we want to have. 61 lah. So 5 tolak 2, 3, 6 tolak 1, 5, 7 tolak 1, 6. Okay?
Okay, doktor. Terima kasih.
Sama lagi? Any other question?